So, this topic is called the photonic bandgap structures. Sometimes it is also called the photonic crystals. We will talk about photonic bandgap structures as integrated optical elements. There is another important field of these photonic crystals called photonic crystal fibers. So, we will not worry much about the photonic crystal fibers at this moment. So, photonic crystal is a periodic arrangement of the structure, a periodic variation of refractive index in various directions. So, they will have very peculiar properties, as we will see soon. So, in this I am showing you 3 different arrangements. We have periodicity in one dimension, the periodicity in both x and y directions, and there is a periodicity of refractive index variation in all the 3 dimensions. So, these can be called as 1D, 2D and 3D photonic bandgap structures. So, one of the important feature of these photonic bandgap structures is all frequencies cannot be propagated through this. Based on the periodicity and the structural and optical refractive index properties, certain frequencies are not propagated, and this could be exploited in making many devices, like devices for communication applications, for sensor applications and so on and so forth. So, I am showing a few cross sections of these 1D and 2D photonic crystal structures. This is a 1D photonic crystal or photonic bandgap structure. You can also identify this with a grating, and you have 2D photonic crystal structures. This is called a hexagonal lattice of this is a square lattice of photonic bandgap structures. This is a hexagonal lattice of photonic bandgap structure, or is sometimes called also the triangular lattice. So, you can compare this analogy with semiconductor crystals. So, in semiconductors, as you know, the atoms are arranged in various ways. Some of them are square and triangular lattices. So, you can describe the properties of photonic bandgap structures or photonic crystals also analogous to electronic structures, but instead of having the electronic properties, you have the optical properties of the structure and optical material properties, which are important here. So, in order to study the formation of the bandgap, you need to consider the scattering of light across all these periodic variations. For in the simplest case, I need to mention that you can, these are all the top views that you are observing, and you can form these structures by lithographic process. You can drill holes in the, you have a, I just to mention that you have a silicon wafer with an oxide or so, and on top of it you can have one more silicon layer, and in this silicon layer you can either create holes or rods. So, if you remove the material in this region, it can be called as a hole configuration, holes in silicon configuration. If you remove the other material, for example, these, if you remove these materials, you come with a rods, dielectric rods configuration. So, this is a square lattice of rods, this is a hexagonal lattice of holes. So, the study of these such structures is complicated, not straightforward compared to the other optical geometries. We need to, the broad technique to analyze such problems is to attack directly from the wave equation. You can write the refractive index as a periodic function of x comma y, and the field also as a periodic function of x comma y. Of course, the propagation direction also could have some variations, and manipulate the wave equation to obtain the values of the fields, the propagation characteristics like betas, and the spectral properties k as a function of the structural parameters, and so on and so forth. But I can at this moment we can say that the study of such a mathematical study of such photonic band gap structures is still not well developed, and there are scope for new mathematical techniques for analyzing these structures. So, we can say that for most of the wavelengths compared to the dimensions optical wavelength compared to the dimensions of the along with the dimensions of the structure. So, if you say d is the dimensional parameter, so the properties depending on how close or away this operating wavelength is with respect to the structural parameters. So, for most of the wavelengths you can say that the light propagates through, and when there is a phase matching sort of conditions, then you can say that those wavelengths, light of those wavelengths is scattered more and form some gaps in the band structure. So, this is a typical band structure of a photonic band gap structures. You have a wavelength in micron on the x axis and transmission coefficient on the y axis. So, you can see that there is a band of frequencies which are not allowed to propagate. Typically in the communication band, this is designed to operate in the communication band between 1.4 to 1.7 microns. You see a large band gap. So, the photonic band gap depends on many parameters of the crystal structure. In particular, of course it depends on whether it is a square lattice or hexagonal lattice, etc. And you have the lattice constant, that spacing, the cell unit cell dimensions, the filling factor, how close these, no, not touching, but how close these are, whether they are very close by or far away, how it is filled and so on. The dielectric constant, contrast between the hole and the outside medium or the rod and outside medium, the polarization of the wave, the direction of the propagation, and so on and so forth. So, this is an example of a, of course, as you know, in like in the electronic crystals, the direction matters most, and it is expressed in terms of the EK diagrams, and in the different directions you express in terms of the unit cells. So, you choose a unit cell and look at the frequency of frequency that it is allowed to propagate along the different directions, and you can plot the curves, dispersion curves representing the variation of normalized frequency along the different directions along the sizes, and you observe that there are several modes that it can allow to propagate. In particular, we would like to notice that there is a band of frequencies which is not allowed to propagate. So, you have a band gap in this region. In this particular example, as a function of the distance or the crystal parameter, it is designed to operate for a values of A ranging from 0.259 to 0.441 micron times the wavelength of lambda. You have the stop band in the range of 1.31 to 2.23 microns. This is a typical band structure, and this is how it is expressed. And of course, for TE modes, TM modes and other configurations, you have different variations of this band structure. So, this is a T band structure for 2D photonic crystal of a hexagonal lattice of air holes in the medium, and this is the direction K direction, this is the M direction, and so on. So, here you have for G of 0.45 micron of the lattice constant, you have radius of 0.35 micron of the whole radius, you have, and the diffractiveness contrast of 2.81 and the whole index of 1. You have these band gap properties. In the TK direction you have 1.24 to gamma K direction 1.24 to 1.67, and in gamma in this direction you have 1.92. So, you observe that in the different direction it has got different properties, and we have to choose the crystal parameters properly in any given design. So, this picture shows the dependence of photonic band gap on dielectric constant or the refractive index of the medium. You have for square lattice of rods, you have a band gap varying with dielectric constant like this, it is almost somewhat parabolic, and similarly for band gap to mid band ratio is shown in this for hexagonal lattice. So, we observe that band gap is increasing with refractive index. So, as you increase the refractive index of the holes or rods, you have more band gap. So, this is an example which shows the dependence of photonic band gap on the filling factor. So, you have a square for a square lattice and for both the hexagonal lattice there is a peak at a particular value of the with respect to radius of the order of 0.2 or so, you have the maximum value of band gap. Similarly for hexagonal. So, both are behaving similarly, but there is some finer differences. For example, this is more symmetric than this, and this has got a lesser band gap than the other one for the similar parameters. So, one of the most common techniques to solve these photonic band gap problems or the design is the FDTD method, which we have seen earlier. We have not gone into much detail about the FDTD method in the when we discussed about the beam propagation method and the passive devices, but I have included here some expressions which could be directly used. You can also find these in some books and current literature. So, basically what you can, this FDTD method discretizes the field in both space as well as time coordinates using different finite difference techniques like central differences or the and so on, and we need to divide the entire area of operation, the grid, in terms of very fine grid points, and at each point you define the field at the middle of the point or at the end of the middle at some particular point and express it in terms of the neighboring points. So, you can finally reduce this wave equation using all these approximations into a set of equations, matrix equations, which when solved would give you the field profiles with respect to the structure. So, in the case of vectorial approach, you have more complicated structure with all the fields taking different values. I would like to mention that there are several freeware developed by different universities. One of the most popular ones called MIT Photonic Band Gap Tool, MPB, which is freely available on the web. You can install and do all these finite difference time domain method easily. So, you can also improve it depending on the requirement of your problem. So, I will describe some devices which we can make using the photonic band gap structures. So, one of the simplest things that we can think of in analogous with electronic crystals is to create line defect. You call this as a line defect where these dots or rods are removed in the form of a line. So you do not have holes in this region, holes are removed in the form of a. So, this acts as a waveguide. So, a line defect acts as a waveguide for light. As we have seen earlier, that if it is a uniform crystal, it will block certain wavelengths, whereas if you make a line defect, as you can see in this particular picture, light could be propagated in the photonic band gap structure. So, this is a simulation which shows the spatial plot of electric field at 1.5 micron wavelength generated from one of the commercial tools. I would like to mention there are several commercial tools also, along with there are several freeware, and the FDTD code also is available, the MATLAB programs and so on, which can be used for such simulations. So, these are some of the parameters which are given here. Large number of points are taken to achieve a good accuracy. In general, we can say that there is a requirement for numerical methods or computational methods for these photonic applications. So, in this particular case you have a high transmission in the range of 1.7 to 1.78 for this line defect. So, 3 dB transmission in the range of 1.28 to 1.23, that means it is quite acting as a good waveguide. So, you can also think of creating a, so this is the band structure. So, this red line in the band structure shows that the light is, this particular frequency is being propagated, you can call them as guided modes. So, the line defect creates a line in the dispersion spectrum. So, the waveguide supports single mode propagation within the band as shown in this example. This is a simulation plot showing various bands, the dielectric band, air band at different points along the k vector. You have spatial plots. So, this is an example of another device made using photonic band gap structures, the bent waveguides. In this particular case, a line defect is created by removing the holes in this region. So, 6 90-degree bends, these are all 90-degree bends are formed by using this configuration. So, recall that it is almost impossible to bend the light 90 degrees in an integrated optic structure, because it would radiate out the light and does not function as a bend. So, with photonic band gap structures it is possible to create 90-degree bends in square lattice. In this particular case, the square lattice of photonic crystal is used here. So, in most of all the cases we observe the spectrum and correlate with the properties of the device that we are looking at. For example, a good propagation characteristics is what is being observed at this point. These are some of the parameters of computation and the computational results. So, this is an example of another case of what is called a microcavity. So, in a uniform photonic crystal, if you create a defect, only one hole is removed, it is called a point defect, and you can use it as a very good microcavity. A point defect in photonic crystal acts as a microcavity whose properties are being studied here. So, in this particular case you see that the light is concentrated in the point defect, and here it is possible to create a structure where you can have modes. So, you can use this if you launch light through this photonic crystal. Second mode, if you launch, it is possible for you to split the mode. You can use microcavities to design resonators or mode splitters. In this particular case we see a peak at 1.46 micron using a single cavity. Using a double cavity you can create a mode splitter. So, there are 2 peaks here corresponding to each of these things, and of course they are coupled. So, the field propagation across this 2 identical cavities has a coupled structure and has very interesting features for many applications. So, this is an example of using a microcavity coupled photonic crystal waveguide to create an ultra sharp filter. So, you have a bus waveguide here, line defect acting as a bus, and this is the C, the point C is the microcavity. A point defect is created which will act as a microcavity, and there is one more waveguide to tap the light out. So, the light is launched into this and can be tagged at this point. So, these are the properties which are shown here. This is a simulator of this photonic crystal waveguide sharp filter. You can see in the spectrum that there is a very sharp peak in the stop band. Of course, this greenish one shows the light propagation in the waveguide. So, the peak is designed at 1.55 micrometers with 4.23 nanometer wavelength spread. It is also possible to create much sharper filters. But of course, as you note there is an important limitation that the Q factors of the resonance are quite small. So, in most of the engineering applications including optical applications, you need Q factors of the orders of several thousands. So, that is an important challenge for the designer of photonic bandgap structure based devices. So, this is the chart which shows how you can decide what wavelength can resonate. You can tune the operating wavelength with various parameters of the cavity. In this particular case, there are two methods of tuning are shown here. You can change the size of the photonic crystal and tune it and get a different wavelength, resonant wavelength. Similarly, you can change the defect refractive index by very small values. This is of the orders of 2.8. You can obtain a very good tuning with refractive index. So, refractive index is varying here from 0.5 to 1.5 of the relative value, and you can get a very good variation in the tuned wavelength. So, these are the plots which show the amplitude or the field variation. So, finally, one more example, you can create a comb filter by using photonic bandgap structures. I am showing you four cavities C1, C2, C3 and C4. So, there is a common bus which brings in the light of all the wavelengths lambda 1 to lambda 4. These are the channels, optical communication channels, each are independently modulated and pass through this bus waveguide, and there are 4 output waveguides for tapping the power, and the C1, C2, C3, C4 are designed such that they resonate at different frequencies. Either the refractive index contrast or the size can be varied so that they resonate at different wavelengths. And here is a simulator of that. Much of the light is going straight, whereas the small fraction of the light is tapped at each of the output ports. This picture shows the peaks which are resonant. So, we observe that they are quite uniformly placed, and the chart shows the channels, their refractive index, their operating wavelengths and other features. So, this is an example of photonic bandgap structures to comb filter. So, this concludes the special topics. The 3 topics that we have considered are the optical MEMS, the ring resonators and the photonic bandgap structures. Thank you very much.